So let's start. So basically we started the second half of the course where we are moving to new additional models, not only deterministic or non-deterministic finite automaton and regular expression. We started to talk about grammars and context-free grammars and context-free languages. And we will continue with the talking about grammars next week. Grammars are important to several fields in computer science. First of all, compilation. When you write compiler for different programming languages, you should know the grammar. You should define grammar, simplify grammar, a lot of interesting stuff. And also natural language processing. Since natural language also has grammar rules for natural language, you and all of us who deals with natural language programming should understand grammars and should encode grammars into our chatbots, robots, or other application dealing with natural language processing. So that is why we actually that is why this model is important. It's not difficult, but it's new for majority of students because you didn't use grammar till now in other courses. So the first part of our practice today is we are giving languages and we are asked to construct a grammar for those languages. I would like to remind you quickly what is a grammar. Grammar from our point of view is a four tuple where we have v, variables. Variables we use to write large letters of Latin alphabet. We have terminal symbols and we use the notation of sigma. It's basically our alphabet. We have a starting variable for our grammar, and we have a set that's sometimes called R from the word rules, and sometimes you can see P from the word production rules. And we are talking about context-free grammar. And in context-free grammar, all the production rules have the following form. We have some single variable on the left side. Then we use a production rule. And here on the right side, we write some alpha, whereas alpha belongs to variable united with sigma united with epsilon. We don't need to tell united with epsilon because I use a star, I use a star sign, so epsilon will be inside, so you can use only V union with sigma, and you can use the clean closure sign. So basically we have one variable on the left side, several terminals and variables on the right side. Also we can use epsilon production. Some variable can derive epsilon. So now you will have to design grammars for languages that we see here. We will solve this question language after language. And once again, I will define the language and I will give you some time to try to solve the question, and then we will solve it together. So our first language is all words that the number of ones in W is even. Please try to define the grammar for this language. I just want to know how are you doing. Okay, I see. Very good. Thank you. So let's move to this question and let's solve it. Wait, no, and polling, I don't know. Okay, clear. So several solutions, first of all, are possible. So the solution I will give is not the only solution, and we will discuss additional solution later. So I defined G1 to be a 4-tuple. As a set V of variables will have two variables, S and A. The alphabet is 0, 1. It was given to us. The starting symbol will be S, and the set of production rules is the following one. Since I need the even number of ones, I'm using the rules with even number of ones that I have one before S and one after S as many times as I want. And then I continue to some new variable A, where A derives only zeros. So I can add zeros before the one, after the one, before the next one, after the next one. Since we know that we have an even length of ones, I can divide the word in such way that the first one I will look and tell that it is in prefix. The last one I will tell that it is in suffix. Then I will go to the substring in the middle, and I will use once again S to derive the substring in the middle, and this way I will continue. Additional grammar that can be used here is that S with A, that actually A will be the same. It will derive only zeros or epsilon. I can have A1 and I can go to some variable B after first one. And then from B, I can once again have a sequence of zeros, one, and after I have the second one, I will go back to S. I can go back to continuation of the string. And then please pay attention that I can have an empty word as a legal string belonging to this word. That is why I'm currently adding epsilon to derivation from S. And from A, once again, I can derive zeros as many times as I want. And also I can derive no zeros. So the explanation for the second grammar. After first one, I move to the new variable, which actually shows me that I have an odd number of ones. After additional one, I return back to S, and I continue this way until I decide to finish. When I decide to finish, I have to finish after even number of ones. So if I have additional one B epsilon, I can finish. But in this combination, I can't have the word ending
Only zeros.
with zeros. Exactly. That is the problem now. So additional possibility that I will give is moving to A as we have in previous grammar. So if I'm moving to A, now epsilon that I added here is redundant and I don't need it. So basically, once again, the idea of the additional grammar that I wrote. For first one, I have odd number of ones and I move to new variable B. When I have additional 1, I return back to S since I have even number of 1s, and I continue to jump between B and S with having as many zeros as I want using A. And then when I decide to finish, I can use O epsilon and finish with the word ending with 1. Or if I have word ending with 0, once again, I can use S. I can jump to A, and then from A, I can derive as many zeros as I want. Any questions? Okay, good. So we will continue to the next language. The next language is relatively the same. So I will give you time to solve. We're still talking about number of ones in W, but now we want number of ones in W to be odd number. Okay, I just want to know if you finished. Okay, half of you finished and the second half does not answer. Okay, so basically we have a grammar similar to previous one, but now we need additional 1 since we want an odd number of ones. So currently an empty word does not belong to our language. So once again, I will use two variables S and A. From S, I will derive once again even number of ones, but then to finish, instead of using the single A, I will use A1A to add additional odd number of ones. So when I want to leave S, if I used the first rule, I have even number of ones. To leave S, I have to use the second rule where I add additional 1. So now I have odd number of ones. And now I actually derive only zeros with, I only derive zeros from A. So basically it's the variation of what we saw before. And sometimes I'm asked maybe one of A's A from left side of 1 or right side of 1 is redundant. It depends how you wrote the language. Here in our case, it is not redundant because I can miss some of the cases. So in the last rule, it is not redundant. In the first rule, maybe I can delete zeros, leading zeros before S and zeros after 1, because if I return or later use it, no, basically we should have possibility of having zeros before the 1, having zeros after the 1, and then using S in the middle. And for the second last one, the even one, we should also give a possibility of having zeros before and after. Additional question I was asked yesterday, can I continue with the same logic that I did in previous example? that I have with additional variable counting even number of ones, and then moving to a new variable where I add additional one and that's it. Yes, you can do the same with additional grammar that I gave you. Questions? Okay. Now we are moving to our third language. And here we are talking about all words W, where the number of zeros in W equals to the number of ones in W. This language is not regular because I can't count until infinity with finite number of states, but I definitely can write a grammar. So please try to write a grammar for this language. Okay, I believe that you solved this question. So basically for each zero I add, I would like to add additional one. So the idea is that for each zero, we add one, and for each one, we add zero. Wait, I moved into incorrect direction. But I don't know if I will see as the first symbol one or zero. So I use the following combination. I have one S0. So for one in prefix, I added zero in suffix. And I have S before one, S after one, and S after zero, because I can add substrings with the same logics that before the one, I can have a substring where the number of zeros will be equal to the number of ones. In the middle, I can have once again the substring where the number of zeros will be equal to the number of ones. And at the end, after the zero, I can have a substring with number of zeros equals to the number of ones. Additional rules that I have to add. Maybe zero will be the first signed and will appear at the prefix. So for zero in the prefix, I will later add one at the suffix. And now, since an empty word belongs to our language, we will derive an empty word and we can use it to eliminate any S that we want from the rules that we have.
Question?
Mm-hmm.
Why can't we, for example, do this?
You can do this, but you will have a problem with word that starts with one and ends with one. Like this one. Since now you have S only in the middle.
Oh,
So
so
one S's should be remained.
So we can add one
Or you can
s.
add
Yeah.
this rule.
Yeah,
Then
but
it
it
will
becomes
solve
okay.
your problem. It doesn't matter. Once again, several solutions are possible for majority of the languages. It's not the single solution. So, because when you use one as 0, 0 as 1, it means that you can't have the same digit or the same letter at the beginning and then the end. And in this language, we can have the same sign, the same letter at the beginning and then the end. So you can solve this problem easily like this.
Yeah.
Adding SS will solve this problem. Okay?
Yeah. Thanks.
Okay. The next one is additional language. And we have the language L4 with 0 in power of n, 1, 0 in power of m, 1, 0 in power of n. Advise you, before you start your solution, I advise you to rewrite this language as 0 in power of n, 1, 0 in power of m, 1, 0 in power of m, 0 in power of n. Does everyone understand that here I have 0 in power of n plus m? The last part, the second part,
Yeah.
after. So when you rewrite this language like this, it will be easier for you to find the solution. Okay. Okay. Good. Very good. Okay. So let's start together solving this question. So basically the idea that for each zero that I add at the beginning, I will add a zero at the end. So this rule gives me this possibility that for each zero in prefix, I have additional zero in suffix. None, and I will continue to this part that I use as a violet color to mark now. So I will add additional one and I will move to the new variable a, which will for each zero in prefix add additional zero in suffix. So here we will have 0 in power of m, 0 in power of m, and when we want to finish, we will add 1 in the middle, which will be the second one in our string. So this language is relatively simple if you know how to divide it 0 in power of n plus m. If you rewrite it as 0 in power of m concatenation with 0 in power of n, then the solution is relatively simple. Any questions? Good. So now we are starting the next set of questions. And here the idea is different. You are giving the grammar, context-free grammar, and you are asked to define the language of the grammar. And in several cases, it is relatively difficult to define. So we will start with the first grammar, and then we will move to the second grammar and to the third. So the idea is you are given a grammar and you have to define the language of the grammar. Okay, I will give additional time. Okay. So let's start to analyze the language. So we know that for each A that we have in prefix, we add B in suffix. So here we have the same number of A's and B's, but A's in prefix are different from B's. But A's in prefix, S, we have to use a new variable A. And from A, we can derive additional number of A's. So we definitely know that the number of A's will be or equal or greater than the number of B's. And that's what we define. We define the language of G1 to be A in power of N, B in power of M, where N can be equal to M or can be greater than M. And both N and M can also be 0, since I can use S derives A and then A derives epsilon. Therefore, we know that M can be greater or equal to 0. Equality to 0 should not be missed. Any questions?
Yeah.
Good.
If I write it a little bit more complicated, will I get points reduced? I
More
mean,
complicated definition, yes. If it's correct, yes, definitely will get your points. But here I can't write a regular expression since it's not a regular grammar, but I can write something that looks like a regular expression. It's not, but at least here the definition of the language is relatively simple. You could also use the prefix and suffix and explain that you have a prefix of A's, suffix of B's, and the prefix of A's has the same or greater length than the suffix of B's. This definition would be also be good and explain what we have. Okay, let's move to the second grammar. Okay, I will move here. So we have G2 S derives A as B, then SS and epsilon. So I would like to check how are you doing. Okay. I will give additional time. I would like to ask a question. Does everyone sees that for each A, I also add B? So the number of A's should be equal to the number of B's? Do you see this? So we definitely know that we are talking about the language where the number of A equals to the number of B's. And from this rule, we see that we add A's in prefix and B's in suffix. But this logic can't be used here because here we have S concatenation with S. So after a set, a bunch of A's, A and B's, we will have once again after B's, A's. But we can use our observation to define the language. So I define the language of G2 in the following way. We're talking about all the words W over alphabet AB. And we have the number of A's in W equals to the number of B in W, that we know. But also, I'm using the following definition. I claim that in each prefix U of W, the number of A's in U can be greater or equal to the number of B's in U. Since I will use this rule, here I have equality. In prefix, if I will use the rule number 1, I can have the number of A's in prefix that is larger or equal to the number of B's. But even if I will have, if I will use the second rule, if I go to the first part, here I will have the number of A's equals to the number of B's. And then if I will use additional letters of the second S, I will definitely add some A's in prefix. And once again, I can claim that the number of A's in prefix can be greater or equal to the number of B's in prefix. So if we write only the first part, we are actually missing the logic of this rule, that for adding A at prefix, we add B in suffix. So that means that we have some logic. Why the A was added before S and why the B was added after S. Okay? Additional definitions can be given. If your definition is correct, good. If you missed something, and once again, what you can miss is this rule, that the A's go to prefix and B's go to suffix. If you miss this rule and you can't add this constraint to the definition of your language, it's not okay from the point of view of defining the language of the grammar. Any questions? The less grammar is really complicated to define. Be in suffix, but then you can jump and use only A's, as many as you want, you can add. And then you can add only B's, and please pay attention that you add A's and B's before S And then when you want to finish, you use a dollar sign. So we will definitely have some sequence of A's, a dollar sign, some sequence of A's and B's. But here, before the dollar sign, the part can be larger, since if I use the rule number 3 and 4, I can add additional A's and B's without adding A and B at the end. So I will give you a time to think about this language, and then we will try to define the language together, and it will be relatively complicated. Okay, please answer if you can. What happens with you? Good. 2 answers, 3 answers. Okay. Thank you. So everyone finished this question? Good. I will give my definition and then I will explain it, and then we will talk about additional possibilities. So I'm talking about the language of G3 to be some prefix, dollar sign, some suffix, where prefix and suffix are defined as words in alphabet A, B. But now I'm claiming the following claim, that if I will have a non-continuous substring of U, this non-continuous substring of U in reverse order, I will see in V. The V is actually some substring that I saw in prefix in reversed order. And why I can claim this claim? Because if I use rule number 1 and 2 here, I define the word concatenation with U reverse. So for each A in prefix, I added A in suffix. For each B in prefix, I added B in suffix, and I continue. This way, using the rule number 1 and the rule number 2, I have the prefix and the suffix is actually a reversed version of prefix. If I use the dollar sign, then I have dollar here. So I will have U dollar U reverse. But now if I go to rules number 3 and 4, I can add only in prefix, only in U, only before S, I can add additional letters which don't have the same letter at the suffix. And that is why I claim that I have a non-continuous substring of U, because each time I use the third and the fourth rule, I definitely don't want to see these letters as the definition of some sequence of U that is actually rewritten in V in reverse order. The question that I was asked several times here, if we will have this question during the exam and we don't see the answer, what do we do? Okay, actually it is a difficult question. It won't be in the exam, but you definitely should define this rule. You definitely should see that here you have some prefix concatenation with some suffix in the reverse order, and we will see those rules a lot in our course. So you can identify U versus U reverse in grammar. You definitely see that you can have a dollar sign dividing between some prefix and some reverse order suffix. And then here in rules number 3 and 4, it was important that you find or you see that you add letters only before S. So you change something in prefix before dollar sign and not dealing with suffix. But definitely this question was a difficult question to define. The grammar is actually relatively okay, we can understand it, but when we are asked to transfer this grammar to the definition of language, it is more complicated and more difficult. Any questions? Okay, if we don't have any questions, we move to the last part of what we should do today. We are given some language that deals with arithmetics. We have the starting variable, which is called E and not S, and it is okay. And we have E derives E plus D or D. D derives D multiplication F or F. F derives E in brackets or T. T derives digits 0, 1, 2 till 9 decimal alphabet digits. The first question that we are asked, what are the terminals in our grammar? And this question is relatively easy to answer. I will give you a moment, but please pay attention that variables you have here. So everything else that you see is a terminal symbol and not a variable. So if I will go to E, I can see plus, and it will be terminal symbol. If I go to rules derived from D, I can see multiplication sign and its additional terminal. If I go to F, I can see the open brackets and the closing brackets, additional two terminals. And if I go to T, I can find all digits of decimal alphabet from 0 till 9. Therefore, in this alphabet, we have 14 terminal symbols. Any questions about terminals? Good. Now the second question. You are given an expression 3 plus 4 multiplied by 5, and you are asked to build, to parse the string, to build a parsing tree, where you will start from E as a root and you will derive the word 3 plus 4 multiplied by 5. And the next question is this parse tree unique, or can you give several parse trees like I did during the lecture because we had an ambiguous grammar? So you have 3 minutes to try to construct the tree and maybe additional tree.
The second one is solvable?
Yes. You have to find the correct order, but it is. Okay, I would like to know how you are doing with 3 plus 4 multiplied by 5. If you finished building the parsing tree. 2 replies are yes and no replies. Okay, 3. Okay, thank you. Oh, everyone solved. Good. So let's move to the 3 plus 4 multiplied by 5. This grammar is actually not ambiguous grammar. Therefore, there is only one parse tree for 3 plus 4 multiplied by 5. So I will show you the result. So from E, we derive E plus D, since we saw the plus sign. From E, we derive D, we derive from D F, from F, we derive T, and then we have 3. So we have 3 plus. Then we look at what do we have after plus, and after plus, we have 4 multiplied by 5. Therefore, from the D, we derive D multiplied by F. And from D, we derive the digit 4. We move from D to F to T, and we have 4. And then multiplication sign. And from F, we derive T, and we derive 5. If we look at the leaves at our tree, we find the given word. We have 3 plus 4 multiplied by 5. So I hope that you managed to draw the tree. The next question, you have to write or to build a parsing tree for 3 plus 4 in brackets multiplied by 5. And exists the solution. There is a parsing tree. It is unique since this grammar is non-ambiguous grammar. But the question is, what should you do first?
I got a really long tree.
It is a relatively long tree. Let's just try to analyze. If I will use this rule with the plus sign like I did before, I can't later add brackets around plus because I already missed brackets. If I go from E to D and I will start with okay, I have internet connection unstable, so if you can't hear me, please tell me. So if I go to multiplication sign with D and F, please pay attention that F is at the right hand side. And I have brackets at the left side of multiplication. So if I use multiplication right now, I can add brackets, but only at the at the right side, not at the left side. That is why I will go from E to D, from D to F, and then I will use this rule as a rule for having brackets at the right side. So let's do the solution together. And yes, you're right. The tree here is a little bit complicated. So I move from E to D. since I don't want, I move from D to D multiplication with F. And from what I see after multiplication, I see that I have a single digit. So I will use F, I will derive T, and I will derive 5. So I finish with multiplication and 5. Then I will go to D, and I told that I can add brackets to D. I can add brackets to F. But I can move from D to F by using this rule. D derives F. And now, if I have F, I can use the rule E in brackets, where brackets is a terminal symbol. So we finish derivation. And then I have to continue with E. So now I have also brackets added. And now I have only 3 plus 4 to derive. So from this E in the middle, I will use the rule E plus D, okay? And then from the first E, I will move to D, I will move to F, I will move to F, and I will derive 3, plus we already have here. And from D, I will derive F, I will derive T, and I have 4. So the tree here is a little bit complicated. If you choose incorrect order, you will be stuck. So basically, if you are asked this question during your homework, or if you are asked this question during the exam, you can write several possibilities, and you will find the tree. Maximum, you will not use your logic to analyze what you should do first. You can just pick all the possibilities and you will find the solution. But basically, the idea was not to use plus as the first sign, to use multiplication, because if I will use brackets E, then everything will be in brackets, but I have multiplication by 5. So multiplication should be before brackets. So that is why this rule was used first. Then I saw that if I will go to F, I can add brackets only at the right side, and I need brackets at the left side of multiplication sign. That's why I replaced the D with F here. D was replaced with F. And in F, I used E in brackets. And E in brackets, you can easily see that you will have the 3 plus 4 combination here if we will use the rule E derives E plus D. Any questions? Okay. If you don't have any questions, we finish for today. We will continue next week with grammars. We will define some sets of grammars, regular grammars, context-free grammars, closure properties of the grammars. We will define some hierarchy of grammars and normal form for grammars. So we still have a lot of things to learn and to understand about grammars. But basically for today, we finished. And you already have the next homework number 8 uploaded to the course site. So if you can, if you have time, you can start solving it.